Here we go, picking up with section 3.2. This is the second video, and we are on example number 4 in your notes. That's on page 11. Today we're going to start by talking about half-life, as you can see here in this problem. That's what we're dealing with. And as I'm sure you have learned in science, half-life is the amount of time it takes for half of the substance to decay. So here it says, suppose the half-life of a certain radioactive substance is 40 days. So that means in 40 days, you're only going to have half of what you started out with. There are 8 grams present initially, so that's how much you have at the beginning. So after 40 days, you would be down to only 4 grams, and so on as you go down the line. It says, find the time when there will be 1 gram of the substance remaining. So it just keeps halving over and over again. Now this one is pretty easy to just kind of do by reasoning it out and not even using the formula here. So let's talk about that, and then I'll show you how you would use the formula in case the numbers were not so easy in a future problem. So you could say, okay, well, I start out with 8 grams, and then 40 days later, I have 4 grams because half of it would be gone. And then after 80 days, I would be down to only 2 grams. And then after 40 more days, which would be 120 days, you're down to half of that amount, which would be 1 gram. So really, 120 days is the answer to this problem. When is there going to be 1 gram remaining? So let's just kind of keep that in the back of our mind. Like I said, I am going to do the problem kind of the algebraic way, so that if the problem has harder numbers than this, you'll still be able to do it. Okay, so the first thing is that whenever you have these half-life problems, what you want to put in for this exponent here is the number of half-lives. Actually, I should have said lives there instead of lives. That's not a word. There we go. Number of half-lives. And that's always just time divided by the half-life. So for example, here you have a 40-day half-life. So in our case, we're going to put in T over 40. That is the number of half-lives. Because let's say you have 80 years. Well, 80 divided by 40 is 2. So that's 2 half-lives. If you had 120 days, 120 divided by 40 is 3. So that's 3 half-lives. So you're just doing the time divided by the half-life, and that's what you're going to put in for T on these half-life problems. Next, the thing that we need to know is that R in half-life problems is always -1/2, because remember, R is the rate at which it decays. Well, if we're talking about half-life, then half of it decays every day or every year, every month, whatever the measurement of time is here. So R is always going to be -1/2. Therefore, 1 plus R would be 1 minus 1/2, which would equal 1/2. So that makes these half-life problems pretty easy, because the 1 plus R, this base, you're always just going to put 1/2 in for that. So in this situation, we would have P of T equals the initial amount was the 8 grams times 1 plus R, which we just said was 1/2, to the T over 40. And then it asks, when will there be only 1 gram of the substance remaining? So for that, you just put in 1 in place of P of T. And then solve for T. So divide by 8. Take the natural log of both sides. Move this exponent down to the front. Divide both sides by the natural log of 1/2. Let's put this in our calculators here. I'm doing that over to the side on my calculator. Natural log of 1/8 divided by natural log of 1/2. That's equal to 3. And then 40 times 3 is 120, which is what we knew the answer was going to be, 120 days. But there's the way that you would algebraically solve that one. Or, of course, you could always graph it. Let's go to our graphing calculators and just check that out real quick here. So on your graphing calculator, you would type in the equation into your y equals. So I'm going to go up here. We're going to do y equals 8 times 1/2, which is 0.5, raised to the power x over 40. And I want to know, when is that equal to 1? So I'm also going to graph y equals 1. Let's see, for my window, my x's here have to do with number of days. So I'm going to go from 0 to 200 days. My y's deal with the number of grams of substance that we have. So it's going to be bigger than 0, but less than 8, because 8 was the initial amount. Here in blue, you see the decay function. In red, you see y equals 1. You just want to find where do those intersect. So second calculate, intersect, first curve, second curve, guess. And again, there's my intersection at x equals 120. 120 days later, I'm down to just 1 gram. So no surprise there, of course. We already knew that was going to be the answer. Next, let's do example 5, which is one in which we have some uninhibited growth of cells. That formula up at the top of your sheet there, I don't have that box on my paper. The formula that we're going to be using is this one right here. A of t equals A initial times e to the kt power. And k is always greater than 0. K is a constant that's representative of the growth rate of the cells. So let's look at this problem here. We've got a culture of bacteria following the law of uninhibited growth. We start out with 500 bacteria present initially, and then we know there are 800 after 1 hour. Now, what the 800 after 1 hour helps us to do is figure out what this constant K is going to be. So what we're going to do is plug in 500 for A initial. And then we know after 1 hour, so when T is 1, and we don't know K, that's what we're trying to figure out, the amount that we then have is 800. So now we just go about solving this for k, so we can figure out the constant. So just like we have been on all of these, divide both sides by the initial amount. So 800 divided by 500 would be just 8/5 equals e to the k power. Take the natural log of both sides. You can take this exponent and move it down to the front. Same process really on every one of these problems. And then actually, if you remember, the natural log of e is equal to 1. If you don't remember that, don't worry about it. We'll get to it again later in the chapter. You could even just type that in your calculator and confirm. Definitely natural log of e is 1. All right, so k is the natural log of 8/5. You could put that in your calculator, and that turns out to be about 0.47. So when we're asking then how many will be present in the culture after 5 hours, we now do a of 5. So we take our initial amount, which was 500. We now know that k is this 0.47 number, and then we multiply that by 5 because that's our amount of time. So you just put that into your calculator. Now, if you can, try not to use the rounded version of 0.47. Use the bigger version that's still in your calculator. You know, if you do the natural log of 8/5, it's like 0.4700036292. That's what I'm actually going to use here. And I'm just going to do 500 times e to that power times 5. And you get about 5,243 bacteria, which is what would be left after 5 hours then. I think I'm going to stop the video here, and we will pick up with video 3 with example number 6.